Let me introduce Jesse. Jesse is one of those students just sort of, on rare occasions, just sort of appears out of nowhere. Most of the time, a faculty member reaches deep into the pool of applicants or pool of students that are already here to find that student that's a great fit for what you're researching, very talented student. That didn't happen with Jesse. Jesse wasn't here. I didn't know him. He just sort of serendipitously fell on my lap. And the way that happened was, and we have a disagreement on this. I was hoping I could contact Roberto. Jesse was at I think it was an APS meeting.
It was not an APS meeting.
And anyways, Jesse was introduced to me by one of my other PhD students, Roberto Colon. And Roberto ran into him. It was a meeting that I insist I was at, but Jesse disagrees. And reported back to me and said, I met this great guy, Jesse Rodriguez, and he's from Oregon State University. He is a triple major. He's a triple degree. Physics, he was a junior at the time, or just
sophomore, after my sophomore year.
He's finishing a physics degree, a mathematics degree, and a nuclear engineering degree. And he's really good. He didn't realize that an undergraduate student could do research, and I convinced him that he should apply to do summer research at Stanford while he's finishing his undergraduate degree at Oregon State. And I kind of said, well, you know, it's really hard to bring an undergraduate here from another school. We can do it, but sometimes we're not prepared. But Roberto insisted, and he convinced Jesse to come. And Jesse came and did research between his junior and senior year on a completely different problem than this. All right, it was on a high energy density Z-pinch machine that I have in the laboratory. And it turns out that he did that for, and that sort of, I don't know if you were planning to do an honors thesis, but that ended up becoming the topic of his honors thesis in physics at Oregon State. And I don't know what transpired after that, but he did decide to apply to Stanford, come to Stanford. He got all sorts of external scholarships, and even got a Stanford graduate fellowship. So it didn't cost me a penny. I think he's the only, maybe Ben also didn't cost me a penny. Not too many students are like that. So Jesse was just a pleasure to work with. He's one of those students that I didn't have to actually steer in any direction. He he was like a Tesla. He just drove on. Anyways, Jesse's topic, Jesse actually contributed to 12 papers that are already in print. I think 3 or 4 from his first author. And he's got 2 or 3 more. I say 3, he says 2. But he's got 3 more to write. And we're going to be first author. So he's been a tremendous contributor to all activities in the lab. Always willing to help students, help his fellow students, and not just here at Stanford, he's helped students at other schools too, do experiments here at Stanford. So with that, his topic is electromagnetic wave manipulation with plasma metamaterials. Jesse, I'm going to hand it off to you, and I want to express my appreciation for you coming to Stanford. It's been a real pleasure.
Well, it's been one of the great privileges of my life, and that's no exaggeration. So thank you for that great introduction, Dr. Capelli. So okay, so let's get started. Here's an idea of what we'll be talking about, a general outline of the talk. Okay, so we're going to start by going through some background. I want to explain to you what each of these words mean in the title. Okay, so you can follow along as to the best of your ability. And then I'll sort of set the stage for where things were when I arrived at Stanford. And then the next section of the talk is talking about taking that groundwork that existed when I was here and pushing it to the next level with three-dimensional photonic crystal style devices and magnetized and devices that incorporate magnetized plasma. And then in the final sort of mostly just second half of the talk, we'll talk about a technique called inverse design that we can use, hopefully, to take advantage of all that complexity in those three-dimensional and magnetized devices. Okay? So let's talk about what do all these words mean: electromagnetic waves, plasma, metamaterials, all right? So in our framework for understanding nature, we have 4 fundamental forces or interactions, okay? The 2 on the bottom, weak and strong force, don't really worry about those. Those have to do with the actions of fundamental subatomic particles, and they're beyond the scope of the thesis. Gravity, you're all familiar with that, so it's holding you in your chair right now. But we're also not very concerned with gravity. What we're going to focus on for this talk is the electromagnetic interaction, or the electromagnetic force, which you may not know it, but it's actually responsible for most of your experiences in life. I mean, it's the reason why you're not falling through your chair. And so you have this little diagram here, which is just a circuit diagram with a battery, and all those arrows tell you which direction the forces push and which direction the energy flows. And we'll talk more about that as we go along. So one of the fundamental properties of matter is charge, which is a measure of how hard electromagnetic forces push or pull on an object, okay? So we represent electric fields with these arrows. And if you have a positive charge, you get pushed along the arrow. And if you have a negative charge, you get pushed in the other direction, okay? And these charges are also sources of electromagnetic fields. So just a static point charge is a source of electric fields. And if charges move, they induce magnetic fields as well. And so when matter moves around, charged matter moves around, you can end up with this phenomenon where when it oscillates, the electric fields sort of break off of the oscillating material and become this propagating electric field. Okay, and an oscillating, propagating magnetic field that's what an electromagnetic wave is. Okay, and so both the light that you see, the light that's coming in the windows and coming out of the lights here, and the signal that your phone uses to communicate, those are both electromagnetic waves. Okay, they're just these little at locals. You know, if you're a single charge, you feel if an electromagnetic wave passes over you, you feel this force that's just pushing you up and down, up and down. And that's what's happening in the back of your eye when light comes in. It's exciting the little molecules at the back of your eye and telling your brain, hey, there's light incident on my eyes. Okay, and so electromagnetic waves are completely ubiquitous in our life, and they're used in almost every modern technology today. So it's fundamental to modern technology. So this figure here is what's called the electromagnetic spectrum, and the way it's organized is we categorize electromagnetic waves by how fast they're wiggling, or sort of how big they are in space. But we'll focus on the frequency, which is how fast they're wiggling, how many times they wiggle per second. Okay, and that's what this line is here. And you can see that all these words you might have recognized before: microwave, radio, X-ray. So lights of different frequencies are used for different applications. So like in the X-ray regime, we can use those to image bones. But microwave radio, these are the types of frequencies that we use to communicate via Wi-Fi and with satellites and radio. This tiny sliver of the electromagnetic spectrum, which has color over it here, that's actually the fraction of the spectrum that you can see with your eyes. But there's the applications in the full spectrum of electromagnetic waves is vast. And my experiments sort of live in this little red circle there. So that's your primer on electromagnetic waves. What about plasma? So plasma is most commonly referred to as the fourth state of matter. It occurs when we inject enough energy in a material to break down its atomic structure. Okay, so imagine you have ice, like solid water. Okay, and all the molecules in that structure are sort of locked together in this static structure. And then when you inject energy, you heat it up, the molecules start to move around, and eventually they break apart and they start to tumble over on each other. They're still stuck together, but they're all tumbling over each other. And that's a liquid. That's like liquid water, okay? And if you continue to heat that up, eventually they move around so much that they overcome the forces that are keeping them stuck together, and they expand to fill whatever container you're filling, and they fly around and bounce off of each other. That's a gas. That's like evaporation or boiling water. But you can go even further, okay? So every atom that makes up a material has a positively charged nucleus, and then it has negatively charged electrons. So remember what we were talking about charges that exist outside of the nucleus, around the nucleus, okay? And it's this closed system. Well, if you inject enough energy into the system, eventually through hard collisions or through the application of a very strong electric field, you can knock those electrons free of the atoms. And so what you have is a positively charged ion, or the nucleus left behind, and the free electrons that are moving about now. And now this is a totally different situation, because these, like I said, these charges, they create their own fields. Okay, and so this charge has an effect on the charges in its immediate vicinity. And if you have some sort of bulk motion of some set of charges, they can create this macroscopic field that can affect the behavior of the material far away. And so plasma has this really strange collective behavior that we see, and it's this really rich physical system that we can study. And we'll talk a little bit about how that interacts with electromagnetic waves later in the talk. So although plasma isn't plentiful on Earth, it's the most common phase of matter in the universe, actually. So on Earth, you may have seen it in the Northern Lights or in lightning, but all stars are made of plasma. And stellar core, even metal is best described as a plasma because the electrons in a metal are pretty much free to move around. But it's this ubiquitous form of matter that we see everywhere. And this plot in particular is just a classic plot where you have the density on the x-axis, so the more dense the plasma is on the right side, and then temperature as you move up on the plot, they become higher temperature. So you have your fusion plasmas on the top of the plot. But so that's what plasma is. Now let's try to figure out what we mean by metamaterials. Okay. So for the purpose of this talk, what I mean by a metamaterial is this material that has an engineered structure that causes it to interact with light in a way that you can't achieve with a normal material, conventional material. Okay. And so what do I mean by this? Well, what you're looking at here is an electric field plot. This is a simulation that I ran. And each of these successive red and blue lines, those are the oscillating electromagnetic field, okay? And the space between these ridges is called the wavelength. Well, this material that's composed of an array of dielectric rods, when you irradiate it from the left with this source, it stretches the wavelength of the light to infinity. It's behaving as a zero index medium is what that's called. And you can't achieve that with a normal material. And so we want to make devices that can have these sort of extreme electromagnetic wave manipulation properties with plasma elements. And the reason we want to do that is because plasma is tunable, and we'll talk a little bit more about that. But so that's what we mean by metamaterials. We want to manipulate waves in a weird way to sort of reach that frontier of manipulating electromagnetic waves. And so the frontier of electromagnetic wave manipulation is optical computing, where computing tasks are performed with light signals as opposed to electrical signals. So what do I mean by this? Well, in this device here, if you send an image of a 5 through so remember, the image is just light propagating through space. So when you send an image of a 5 through this device, the light gets steered towards a detector that says, hey, you're looking at a 5. And the way you would do that with a conventional computer is with a convolutional neural network. It would involve a lot of computation. And in this case, the computation is being performed at the time it takes for the light to travel through the device. And light travels at 670 million miles per hour. So it's essentially instantaneous, right? So with optical computing, you get higher bandwidth and speed in comparison to solid state electronics. It also is less prone to component heating. This is important because we have to make our computer chips flat because they produce a lot of heat. If you created a three-dimensional stack of transistors, the material would just melt. And so you can, with optical computing devices, you can create these three-dimensional structures that can do something really complicated. Like this is a matrix vector multiplication, which is just really multiplying and adding a bunch of numbers. But with this device, you can encode an arbitrary matrix in this dielectric permittivity domain and then perform matrix vector multiplication. So the reason why we want to make these types of components out of plasma or push towards being able to make components out of plasma like this is because plasma has this tunable dielectric response. And we'll explain what we mean by that later, but really what that means is that instead of the functions being frozen in for these types of objects here, you could have a plasma structure that you could encode an arbitrary matrix into and do arbitrary matrix vector multiplication perhaps, or have more than one different types of classification you could do here, like handwritten digits and handwritten letters. So that's why plasma might be particularly well suited for this type of application. So what do I mean by being able to tune plasma? Well, the key attribute of plasma is that by tuning the plasma frequency, we can make the elements or devices either stretch or speed up electromagnetic waves or act like a metal in a non-magnetized plasma. So what you're seeing here plotted is this simplified model called the Drude model that actually does a fairly good job of approximating the behavior of our experimental plasma elements. And you have this key parameter here that's called the plasma frequency. And when it's squared, it's proportional to the plasma density. So you can change the plasma density of your plasma elements by providing more power to them. If they're laser generated, you up the laser power. Or if they're in a discharge, you could supply more discharge current. And this value here, the permittivity, characterizes how the material interacts with light, really is what it's doing. And the point of this plot here is this is plotting that epsilon here. And what happens is that by increasing the density, you move to the left on this plot, okay, which is a plot of frequency normalized by omega p, and you can enter this metallic regime. So your plasma looks like a metal; it's shiny and reflective. But if you decrease the density, the waves are allowed to penetrate into the plasma, and they're stretched out. And if you continue to increase the density to very, very low values, the plasma becomes transparent. And so by varying the plasma density, you can sort of, and especially playing around this regime, right around this line, you can really strongly affect the way your material or your plasma elements are interacting with light, okay? And so that's the kind of tunability that we can take advantage of. And then when the plasma is magnetized, we can actually attain permittivity values beyond the limits of the Drum model, so beyond that vacuum dielectric response, and we can approximate the behavior of conventional dielectric materials like ceramics and whatnot. Okay, and the way we do this is by utilizing resonances at key frequencies, and we'll talk more about this when we get into the magnetized section of the talk. This on the left here is what's called a dispersion diagram. It tells you what kind of modes are allowed within your medium. And then here's a plot of the permittivity in a specific mode. So when I got to the Stanford Plasma Physics Lab, our lab was engaged in the construction of plasma-based optical devices that utilized photonic crystal structures. So basically just periodic arrays of plasma rods or elements. And this is actually a laser-generated microfilament array. And then in this case, you had this resonator device. And they were kind of like resonators, which means that they had a really strong response at a single frequency. Or they were waveguides, so they were steering light through these 90-degree bends. And then there were bandgap devices, which is a type of device that disallows propagation through a certain frequency range. So imagine you have a material that doesn't let green light through at all. That would be like a bandgap device. And so this is where we were. And we were kind of, when I arrived, it was like, okay, how can we push this to the next level? What's the next logical step? Well, the next logical step is to increase the dimensionality of the device, okay? But first, I should talk a little bit about what do I mean by dimensionality. So this slide sort of describes what a photonic crystal is. And a photonic crystal is a periodic dielectric structure. And when you have that periodic structure, it enforces the fields that propagate through the structure to be periodic as well. And so, and for those of you who are familiar with partial differential equations, for example, you're enforcing periodic boundary conditions. So it's like solving the partial differential equation on a finite domain. And you know that if you solve a wave equation on a finite domain, you're going to get a discrete set of solutions. And that's what these lines are in this plot here. These are the allowable propagation modes. And so when I talk about dimensionality, I'm talking about the number of directions upon which you have heterogeneous properties. So if you move this direction, you're changing with different material properties, but if you move into the page or up and down, you're not seeing any changes. In 2D, you have two directions, both into the page and across the page, where you see that heterogeneous case. And the important thing about like a 2D device like this is that the polarization of light, which is the alignment of the electromagnetic field, is actually very important for devices of this. So if the electric field is aligned on the homogeneous direction, this is called a TM mode, it gives you a totally different type of propagation than the TE mode, which is where the E field is across the columns or in the heterogeneous direction. And so the red and blue lines are the different propagation modes that are allowed for those two different types of polarization. That becomes important. So these dispersion diagrams may look complicated, but for practitioners, we look at this and we can actually come to conclusions about what kind of propagation structures we'll see in the device just based on the topology or the shape of these different dispersion diagrams, okay? And we'll talk more about that in the future as well. So the first thing that we did is we created this three-dimensional device that was composed entirely of plasma elements. So here's the simulation domain here. This is where the electric fields are entered into the domain. And this is called a wood pile structure of photonic crystal. And you can see a photo of the device here. It's a bunch of plasma rods that are sort of stacked 90 degrees to each other in successive layers. And this is a bandgap device. So it's designed to disallow propagation at a certain set of frequencies, in this case from about 2.7 to about 4 gigahertz, okay? And the important thing that we observed here is that the phenomena that were occurring for either polarization, we could get this synergistic interaction between those two types of phenomena. So like I said, you get totally different propagation characteristics for whether you're across the rods or along them. But here you have both types at the same time. So if we look at this transmission diagram, so the lower the line is, the less light's getting through. If we just turn the horizontal on, that's the orange line, or just the vertical rods on, meaning activating the plasmas, we get this sort of attenuation. But if we have them all on, we actually get this point where we have more attenuation than we would have gotten if we just put those two filters in series with just the vertical and horizontal. And what that suggests is that the coupling into these modes, these are called localized surface plasma modes, that coupling happens for the TE polarization, and then the normal Bragg scattering, destructive interference type of attenuation in the other polarization. Those two resonances or band gaps were having a sort of interaction that caused a greater attenuation than you would be able to get by putting the two in series. So you can see that by going up to this increased dimensionality, we can get a performance payoff that is more than you would assume. So that was the first thing that we showed. So then we thought, okay, well, what if we magnetize our elements? What might be possible in that case? So I should say that some dispersion topologies, meaning the shape of these dispersion diagrams, result in very strange behavior. So this type of crossing here, we have a linear crossing and it's conical when you look at the full dispersion surface. A triple degeneracy at the k equals 0 symmetry point. And in a photonic crystal, this is all start to get a little jargony. But the idea is that when you see this structure in a square lattice photonic crystal, this is what produces that zero index medium behavior that I showed you in that earlier metamaterial slide. And this kind of device is strange because the electric field has an infinite wavelength inside the material. If you embed in a finite sized object in that material, from the wave's perspective, it looks infinitely small. So it just goes right around it as if it's not there. And so this object is actually cloaked by this device. The waves coming out of the material of the system look as if there's no material there or object there at all. You can't tell it's there. So we were looking at something like this and we're like, can we make this out of plasma? Well, in order to do that, we need to be able to have our elements in our photonic crystal have a dielectric constant which is greater than 1, right? Which you can't do with a non-magnetized plasma. So what we had to do was try and take advantage of this resonance in the right circularly polarized branch of the magnetized dispersion. And so if we can tune the magnetic field and the material properties just so, the plasma densities, and work in this configuration where we're irradiating the photonic crystal along with the pointing right along the applied magnetic field, we should be able to observe these sort of cloaking behaviors, okay? But there's a problem here. Like I said, it's this polarization issue. The right circularly polarized light, instead of the light wiggling just up and down like this, it spins. That's what it's doing. And that's a superposition of both polarizations at the same time. So you actually need this dispersion topology, this shape, this type of linear branch crossing, to occur in both polarizations at the same time. And so we need to find a Dirac point, which is what these crossings are called, that is coincident in both polarizations for the exact same set of material properties and frequency and device parameters. And somewhat miraculously, we were able to find such a pair of DPs. And this is what we see on the bottom right here. This is the two for the two polarizations lying on top of each other. And when we operate at that point with a magnetized plasma right on that resonance, we see this type of behavior. So it's very strange because we're operating at a higher order mode. So you get these strange scattering structures that it's not a perfect cloaking device, but it removes the shadow behind the object, the wake. So when there's no crystal there, you get this sort of wake behind the object, right? And this is the signature that there's something there. And you can actually reconstruct what kind of image might be by looking at this attenuation of the intensity of the light. But when you encase it in this magnetized plasma photonic crystal, you can see that in both polarizations the wake is mostly removed. So it sort of masks the device. It's a very strange result that you can get with a magnetized plasma. And so another strange topological phenomenon that can be observed in magnetized plasma photonic crystals is a unidirectional edge state. So An edge state, a unidirectional edge state is this type of mode that when it propagates on the edge of a photonic crystal, it only moves in one direction. Even if you have some sort of strong defect in the boundary, it'll happily propagate around the defect and continue going because it's said to be topologically protected. But really what's going on intuitively is kind of easy to understand in the context of plasmas. So in our lab, we've shown via electric field measurements that our cylindrical gaseous plasma sources have a pronounced gyrotropic response, okay? So we magnetized our sources and we mapped the scattered electric fields experimentally. And we showed that even when you use this bulk, uniform magnetized plasma model, your elements produce the same differential scattering that we expect. And so what happens is if you excite an electromagnetic field right at this boundary, you have a mirror on the left and the photonic crystal in a band gap on the right, the light's not allowed to propagate into the crystal because it's in the band gap. But at a micro level, this scattering is sort of differentially happening in one direction. And it just continuously happens like this. And so the light has nowhere to go but in this direction. And so you end up with this one-way state. So we were like, okay, can we actually manage to observe this in a plasma photonic crystal experimentally, which has never been done before? So the way that we went about doing this was by creating this 3D printed scaffold with 3D printed walls that have been electroplated with copper to serve as that PEC or mirror boundary. So this is what the bottom right is where you can see the actual scaffold itself. You can see the electroplated walls, and then each of those holes is where the plasma discharges go. And then we have these holes in the walls where we can insert a field probe and try to detect those edge states. Okay, and we actually just irradiate the array with these microwave horns and just use a vector network analyzer to see what our transmission looks like. And so we simulate this setup with our experimental parameters and a conservative collision frequency on the order of about 0.5 gigahertz. And we actually see the presence of this one-way edge state. So what I mean by conservative is that in reality, our collision frequency is likely to be higher. It's about 1 to 1.5 gigahertz. But to see those fields in a field simulation, you typically have to go to zero. You might even have to set the collision frequency to 0 to be able to observe them in a field simulation. But in this case, at 0.5 gigahertz, we can see that when we change the magnetic field bias, we get these one-way propagating edge states that happily go around this sharp defect here, in both cases in either direction, depending on which direction the bias is applied. And then when there's no magnetic field, you actually have dispersion modes that exist. The band gap doesn't exist there. And so the light can go into the device. So we looked at this and we said, okay, this is promising. Let's actually make the measurement. And when we perform the antenna measurement, we observe about a 10 dB isolation in the correct frequency band between the cases of the magnetic field oriented and the positive Z and minus Z directions. So these are the actual band diagrams that we calculated, okay? And so when the magnetic field is off, you just have a degeneracy that exists this frequency. But when the magnetic field is activated, a band gap opens up. That's what these red bands are. And then you can see that at precisely about that frequency range, we have this strong signal in the correct direction when we measure the field on the edge of the crystal here. And so, this has been demonstrated with like solid state ferromagnetic type of materials, but it's never been demonstrated with a gaseous plasma. And even though 10 dB might seem like not a lot of isolation for a collisional plasma, this is actually a fairly intriguing result, and sort of shows that the key takeaway here is that when we magnetize our plasma elements and create this structure with them, we can actually get this bulk gyrotropic behavior from this effective medium that's created by that structure. And so we can create bulk gyrotropic media, which is typically very difficult to create, especially with like a magnetized plasma type medium, okay? So now we saw that we can get this enhanced performance in these weird, when we go to 3D and we can see these weird types of phenomena when we magnetize our plasma. It's like, okay, well, let's try to find a way to take advantage of all that complexity. Well, to create the devices that follow, we use a technique called inverse design. And that's exactly what it sounds like. So you choose the objective behavior that you want, the function that you want, and then you encode that mathematically, and then you map that to a set of parameters that encode your device domain, the physical domain where your fields are solved. And you run a bunch of simulations, and you just adjust all those parameters until your domain results in the performance that you want. Okay, and so the most sophisticated inverse design devices today can actually achieve grayscale values for the dielectric constant. So this is actually a figure from a member of the committee. So plasma can tune continuously between dielectric values like this element here, and these types of devices are great because they're low loss and they're super high efficiency. But they still can only perform one function. Once you create this, the function is frozen in. Now, with the plasma, you can actuate the functionality. You can turn it on and off, and you can also reconfigure it to do many things. And so that's why we would like to make devices that they use inverse design with plasma elements. Okay, and so the general process is described by this flowchart here. So you have this parameters. Okay, parameter vector rho. And every parameter here maps to a single plasma element. It tells you what the plasma frequency of that element is. And then you encode your device domain and create this relative permittivity domain. Okay? Then you feed that to a field solver with some source. And then you get your electric fields out. And then you look at your electric fields and you ask yourself the question, do these electric fields look the way I want them to look? And the way you do that is by plugging them into an objective function. That depends on your electric field, which depends on your relative permittivity domain, which is encoded by your parameters. So then you can evaluate a gradient of that objective with respect to your parameters, and then iteratively improve your device over successive iterations. Okay, and then this is sort of like a cartoon of what you're doing. So you have the parameters, they map to the different elements, and then you get the performance that you want. So when we went on to this investigation, we were like, okay, let's just start with something really simple. We have uniform plasma elements with no non-ideal factors. They're just collisionless Drude plasmas. And we also have these square waveguides that are not optimized to couple to free space or to the plasma elements. They're just there. And let's see what happens when we apply this inverse design methodology to this configuration. So we have these two types of functions that we wanted to demonstrate, which is like a directional waveguide or beam steering device that can direct the light through a 90-degree turn or straight through the device and preserve the input mode. Or a demultiplexer, which is a device that takes one frequency of light. If you send one frequency or color in, it goes to the top exit. And if you send another frequency or color in, it goes to the bottom exit. Okay? And so the low loss waveguide or the beam steering device is the simplest objective. And these are the results. So let me explain what you're looking at here. So first of all, you have the two different polarizations, because remember that these are now two-dimensional geometry devices. So you have different responses for either polarization. And then you have the electric field magnitudes here. And then you have the relative permittivity domain on the right. And basically what this is you can see each one of these circles is a plasma element. The darker red it is, the higher the plasma density of the element is. And then the closer it gets to gray and then black is like the plasma is being turned off or lowered in plasma density. And so you can see that we get this really good performance in all cases. And then I also want to point out that this distribution of plasma densities, you would never, I mean, you might be able to tell if you looked at this what the device did. You might be able to say, okay, it's probably going to direct the wave to this, but you wouldn't have chosen this via intuition. And so that's the type of thing that you often see with an inverse design device is you get this completely unintuitive device structure that you wouldn't be able to achieve through intuition alone. So in each of these cases, the operating frequency is, the normalized operating frequency is 0.25. The reason why we lowered these operating frequencies so that we could cap our plasma frequencies at conservative values, on the order of 6.5 gigahertz. This is a plasma density of 5.24 times 10 to the 11 per centimeter cubed. This is actually a very conservative value. I mean, we should be able to get we expect to be able to get our elements to go to even up to 9, 10 gigahertz. But we wanted to keep a conservative cap here to maintain the experimental feasibility of these types of devices. So the demultiplexer configuration, remember, sends one frequency up, another frequency down. It also gets really good performance with the exception of the low frequency transverse electric polarization. And the reason for that is because of the presence of these modes that I mentioned earlier called localized surface plasmons. They're basically just a way for, they're a loss mechanism. They're a mode that the incoming light can couple into, and that just becomes lost. Whereas for these types of devices, we're trying to promote mode preserving, and we want to get as much energy to the correct exit as possible. So the TE polarization, I should say, is not really a good operating polarization for these types of devices. But I should also point out that multiplexing and demultiplexing are actually really important functions for achieving a high degree of parallelism in optical computing devices, because you can encode different information in the different frequency components and split them apart and put them back together. Okay, so that's the demultiplexer performance. And so, okay, we got those results with the idealized model, and we're like, okay, well, let's actually try and figure out if we should be able to build these in the lab. So we refined our plasma element model. We incorporated a non-uniform plasma density profile. We introduced loss at a collision frequency, which is about what we expect in our experimental devices, and we also had, you know, the quartz envelopes of the plasmas, as well as we made sure that the devices were resistant to random perturbations, so it was robust to experimental error. And so, with these non-ideal factors considered, the waveguide and the demultiplexer still function well. You know, you get a little bit more loss, you can see, but nothing disqualifying. And it's also worth pointing out that these are much more difficult to optimize now. You really have to introduce all the non-ideal factors one piece at a time and re-optimize the device, but you can still get the performance that you want, okay? So we thought, okay, we think we can build these things and that they'll actually work. But first, we took a look at if we want to look at the device's complete potential and we remove all the non-idealities, we can actually achieve the function of a Boolean logic or a fully functional logic gate. So these are the logical bits on the left here. So an AND gate, you know, if you only want the true signal to be illuminated when both of the bits are active. And you have the OR case on the right. And so this is actually a really interesting result, because the Boolean logic is an inherently nonlinear objective. And we're using all this linear physics, all these, you know, these 100 linear elements are able to achieve this nonlinear objective. And so it really shows the potential of being able to use these devices, because even in this very simple configuration, we can get this really complex device functionality by using this inverse design methodology. So, okay, so then let's figure out how are we going to actually build these things. Okay, well, the first order of business is that you have to develop a map between the power supply settings for each of the plasma elements and the plasma frequency of the element. Okay, and this is difficult in practice for a number of reasons. We get these discharges are custom fabricated for us, you know, from a factory, and the information about what the fill pressure is proprietary. So they can only give us a range of fill pressures. You can't measure the plasma density of these types of discharges using optical diagnostics, because the plasma densities are too low, and we can't put a probe in there because the discharges are prefabricated. So our best option is to measure the discharge characteristics, meaning the voltage and current through the bulb, and then feed that information to a well-validated kinetic model of a gas discharge called Boltzig plus. And so what we do is we vary the fill pressure, okay, and like the gas temperature through our best estimated range, and we get all these different cases for the mapping between the power supply voltage and the plasma frequency using this kinetic model. And we put all those together, and then we create this sort of a quasi-experimental fit where we have this envelope with this fitting parameter k that sweeps through all of the high plasma frequency cases and the low plasma frequency cases. And then we also added a scale parameter 0.8, which allows you to we saw that these plasma frequency values were a little bit higher than we expected. So we added that scale parameter value so we could maintain the same sort of trend as a function of power supply voltage, say, but perhaps get values that were closer to what we expect. And so now we have this mapping. So we can set the thing, and I should say that what I mean by current limited and voltage limited in the previous slide, these are the two different operating modes. So it turns out that when you set the discharge, you can limit the voltage and let the current sort of stabilize to whatever value it wants to be at. And that gives you all these high plasma density training range. But if you instead allow the voltage to stabilize and limit the current, you can enter this lower operating mode with these DC ballasts that we have. and access these lower plasma frequencies. So that's what I mean by those two modes. Sorry, I didn't mention that. So this is our mapping, and we can take this and we can encode this in a library. And when we take the parameters from our computational optimization, we can then address each of the individual plasma elements and tell them what the power supply settings should be to realize that plasma frequency from the in silico or the computational optimization. So this is the actual system, a diagram of the system. So you have your plasma discharge on the left, or on the right, sorry, and it's connected via DC ballast circuit to your DC power supplies, which are all on these communication buses. These wires that carry serial communications that come from a library that I wrote to individually address each of the elements in the device. Okay, and this is what it looks like. So you have this big rack of power supplies. There's 100 on this shelf. And then they're all connected to these ballast circuits, okay? And then you have to get all the connectors to connect to the correct bulb over here. And then, you know, when you can set the array according to your optimal parameters. You can see this is the array activated with, you know, various different plasma densities throughout the elements. And then the entire thing is sort of enclosed in this makeshift anechoic chamber.
So what's the scale?
What's the scale? These bulbs are about 30 centimeters. So you're talking like about this big. Okay, and so we wanted to validate our inverse design results, and you might have noticed that we moved to this triangular lattice, this hexagonally shaped array, as opposed to the square array. The reason we did that is because you tend to get better effective medium behavior with a triangular array, so that's why we made that switch. But basically, we have this configuration here. We have 3 different horns. Or sources, 2 and 3 lower and higher, and then those are the parameters. And this is what the simulation domain looks like. The red lines are where we evaluate, like these are like loss surfaces, so we can discourage leakage from the device, and then we can either promote or discourage propagation into the correct or incorrect exit. And so the preliminary results were quite promising. So what you're looking at here, this is the beam steering objective on the top. At 6 gigahertz, it's supposed to steer the light to port 2, okay? And this plot on the right is the transmission for a lot of different frequencies. So this is happening, this optimization happens at a single frequency. This is the transmission for many different frequencies. And it shows that at the propagation frequency, the transmission in port 2, that's S21, is higher than the transmission in port 3, that's S31 here. And this difference between these two is called the isolation. And we want that isolation to be as big as possible. And in the demultiplexer case, the 2 different operating frequencies are 5.5 and 6 gigahertz. And you can see that you get the sort of structure that you want where the transmission is higher 5.5, and then the 2 lines cross and the transition is higher at 6 gigahertz for S31. Now there's a couple of things that we can observe right away. So the first thing is, it's like, what's going on here? And isn't this a better demultiplexer for 8.05 and 7.5? And the answer to that is yes, and it's exciting because it shows you that the dynamic range of this device allows you to get these strong isolations, but it's discouraging because our model, our element model, the simulation model. This is a 2D simulation where this is an actual in reality, obviously a 3-dimensional device, and so that has electrodes and all these other factors, and so it shows that by doing the optimization on our computer, we can't actually recover this strong performance. So it was kind of a mixed result. It's like, you know, we can't do it computationally very well. It still works. We get the performance we expect, but we could do much better, and we're not able to do that with our numerical model. So this is where the fact that these devices are made out of plasma is such a great thing, because we can actually just perform the optimization completely in situ. And I wanted to take a moment actually to say, though, that to reiterate that if you try to create these devices with physical intuition, it just doesn't really work out. So in this case, I tried to set the plasma densities of the elements to perform this demultiplexing objective the best way I could come up with my experience with all these different devices. And you know, in both the simulation and the experiment, you don't really get the performance that you want. These vertical lines indicate the operating frequencies. But even again, at the other frequencies that we didn't intend to have any sort of strong performance, we're getting some weird structures. So this just shows that we still get better performance using the computational optimization method than we get when we use the intuition method to develop or to design something like a demultiplexer. But it's not quite taking advantage of the full dynamic range of this system. And so, like I said, but with plasma, because we can dynamically change the plasma density of each of the elements on command, okay, with experimentally, we can actually optimize the device completely in situ, completely experimentally, okay? So this time, the optimization was carried out using this optimization objective that just looks at the transmission in the two ports, and we use the same sort of gradient descent algorithm, but completely experimentally, okay? And in this case, you actually get isolation which is 20 dB higher. It's almost 30 dB at the operating frequency. This is just the beam steering objective, okay? And which is actually a lot better than we get in the in silico case. So again, on the right side, the whole right side of this plot is the in situ or experimental optimization. The left side is the in silico or computational optimization, okay? So if you look at the real ground truth experimental results, you get 100 times better isolation when you optimize these things experimentally. But you know, if you take the optimal parameters from the experimental optimization and feed it back to the in situ, or sorry, to feed it back to the simulation, you can see the performance appears to be worse in the simulation. So this just sort of reinforces our notion that the model is not quite there, both either the model of our plasma elements or the fact that we're using a 2D simulation. We're never going to be able to get the fidelity, or not never actually. We're currently not able to get the fidelity that we can, but we can use performance like this to then try and improve our model. We can try to reproduce this performance using our numerical model, and then maybe we could do the optimization more effectively in silico. But yeah, so this is a really exciting result, and what it tells us is that by using plasma metamaterials, okay, we can optimize our devices completely experimentally. We don't have to run these costly simulations over and over for many iterations. We can just use the ground truth. And so if we incorporate that technique with these types of really complex behaviors that we see in magnetized plasma photonic crystals with three-dimensional structures, we might be able to move towards and push towards these crazy applications like optical computing devices. So that's the main idea that I wanted to convey. Now, before I completely conclude, I want to say thank you to a number of people. So of course, I want to thank the committee for your time. I mean, especially the readers. I know it's a long document, and I really appreciate your time in going through it with great detail. My advisor, Dr. Capelli, you know, when neither of my parents went to college, and neither of their parents went to college. You know, so my parents they created this generational turnaround where their parents and for every generation beyond that had to work hard with their hands to survive. And my parents, you know, I grew up with this expectation of I'm going to go to college, but I didn't have an academic path in mind. So a lot of times when I was throughout this path, I was just like, what am I doing? But you know, Dr. Capelli was very good at I always felt like he believed in me, and he made me feel like I was doing the right thing. So I thank you for that. And I want to point out important mentors that did the same for me in high school, Mr. Lampert and Warner Strepo, who sent me that conference that I ran into to Roberto. So who's right here? So I have to point out Roberto, but I also want to thank all the members of the SPPL, all of you guys. I mean, collaborating with you, you guys are all so talented and smart. It's been a privilege to work with all of you. When I first came to Stanford, I worked with Tom Underwood, and he really showed me what I could aspire to. He was so competent, and he was kind of showed me what I could maybe become through my time here. And I also, of course, have to point out Ben. I mean, I spend more time with Ben than perhaps my wife in the last 5 years. We've worked together on all these things. He's become, you know, my best friend down here, and he's giving me just a wealth of fun conversations. He's a very interesting guy. So I also want to say thank you to all my friends. I've never been a super social person, but I was thinking about this, and you know, I've really made some amazing friends down here. A lot of these friends are really my wife's friends that I just borrow from her. But you know, we got our dog Juniper while we were down here, and we made this great community of dog parents that we became very close friends. And I also have, you know, some of my undergraduate friends on the right here. All of you have made this whole journey really fun. I have to say thank you, of course, to the Moore family, my in-laws. They've been, you know, they just really accepted me into their family and been super supportive. Helped Leanne through this process tremendously, coming to visit and flying her home, and just always making me feel at home when I'm with them. I want to thank them for that. Of course, my siblings, my sisters. You know, it's funny when you're growing up, your siblings end up impacting who you become just as much as anybody else, you know. So my big sister, she taught me how to be loyal and thankful and grateful. And my little sister made me want to be a good role model for her, and I'm so proud of her. So I thank you guys for helping me along the way. And then, of course, my wife, you know, she didn't want to come here. And she's lived in a 400 square foot apartment with me for 5 years, and she's pregnant with our first child. So she's sacrificed a lot for me, and I just, you know, obviously, goes without saying, I couldn't do this without you. So, and then of course, I want to finally, this is the last, I promise. I want to acknowledge all the people who kind of came before. Both my parents, like I mentioned, you know, the life that I've lived is unprecedented in my family. And it's a miracle. My abuela, she passed away while I was here. And, you know, she had a hard life. And now I get to, they all worked with their hands, and I get to think about the things I'm passionate about for a living. So I'm really grateful to all of you, and thank you for everything you've done. So anyways, I'll wrap up there. This is the publications that we produced during my time here, the journal articles on the left, and then conference presentations and posters on the right. And then I'll ask if anybody has any questions, both in the Zoom meeting or in person. If you guys have anything you'd like to ask.
Okay, so at this point, we open it up to the general audience. The committee will refrain from asking questions. So, go at it. Who wants to start?
My dad.
Your dad wants to start.
I have a question.
Yes.
Mr. Jesse Rodriguez the sixth. He doesn't acknowledge that, but he is the sixth. You did a fantastic job, son. It seems in your 3D plasma photonic crystals, you have localized surface plasma. Can you explain to me what these are?
That's a great question. Localized surface plasmons are a type of mode that you can couple into with finite elements, plasma elements or metallic elements that have a negative dielectric permittivity. Okay, so if you have a small plasma element with an electromagnetic wave that has a wavelength which is much larger than the element, you can couple into these modes that are called localized surface plasmons. And really what they are is they're a resonance that can occur where the fields. What happened?
Why don't you drive?
Okay. So you have your plasma element here, and you have your wave that comes in, but the wave has a big wavelength. Okay, and what it does is it excites these charge oscillations on the surface of the element. Okay, because remember the element is metallic, and what that ends up looking like is you get these really closely confined electromagnetic fields around the elements. Okay, and it's just really in essence it's a path for the energy to take when it irradiates your device. So it's useful if you want to make a bandgap device because these resonances happen at certain frequencies. And so if you create a bandgap device, you can tune the plasma density of your elements so that the coupling into this mode happens at a certain frequency, it doesn't make it, and then the wave doesn't make it through your device as well. So you get a bandgap, transmission bandgap.
Oh, I think I need to hire your father to
It's all genetic.
There's got to be some more questions.
Yep.
Ben.
Jesse, can you talk more about how you did the optimization? Kind of like walk us through. Like, was it just one time did it optimize, or how did the machine actually work?
The experimental optimization. So this is something that we can get into definitely more in the private session because it's a little complicated, and it's part of the reason why I didn't show an experimentally optimized demultiplexer device. But really, what I'm doing is in essence, I'm taking the parameters for each of the elements in the device, and I perturb them in a random direction. I either turn the plasma density up a little bit or turn it down a little bit, and then I observe how the objective changes when that happens. So if you change the plasma density of one of the elements, you increase it, and then your objective goes up, you get better isolation of the frequencies you want, then you might want to adjust the plasma density of that rod to be higher. And so basically what I'm doing, I'm just doing that very quickly throughout all the elements, all at once computationally, and then that's how you step forward to that better performance. So that's the general idea. Max?
So you're computing a discrete gradient?
Basically, yeah. But it's yeah. So it's essentially, it's a little bit more. It's actually a little bit more stochastic than that because I'm perturbing many elements at once. So it's not a perfect gradient. There's some effects that can happen that can cause the objective to not increase monotonically. For example, the objective kind of varies as it works up, but that's the idea.
Any other questions?
Max, I think Max had one more. Yeah, go ahead.
Would the ultimate goal for a device like this to be able to do arbitrary matrix multiplication or Boolean logic?
Well, that's kind of the beauty of these plasma metamaterial devices, that you might be able to have. Imagine you have an entire building that's composed, just filled with plasma elements, and it's just completely complex, and you can have all these different configurations that do different things. These optical computing devices, it's already been demonstrated with solid state components that you can get faster matrix multiplication, like general matrix multiplication on an optical computing device than you'd be able to get with a conventional computing device. So what I sort of envision is that you have these specific tasks that you want to offload to this application-specific component that may have plasma elements in it that can allow us to continue to scale our computational capacity beyond this sort of physical limit in Moore's law that we're running into right now. So that's what we're pushing towards. Yep.
So on that topic of scaling it up to a very large metamaterial, what would the power supply look like for that? Because I imagine that you might progress past stacks of DC power supplies and maybe more towards something automated. Have you thought about how that might be implemented?
Yeah, I mean, my hope actually for the next phase of this is to not have to go to much larger devices with more power supplies, but actually to have a marriage between the complex lossless dielectric structures and plasma elements that can tune the performance of those and also incorporate different types of plasma generation methods like laser generated plasma, for example, so you can get a lot higher densities. But to answer your question, I'm not sure. I think you'd have to really fabricate some custom components. You can't really buy things off the shelf that have power supply with 100 channels that are all programmable. So this is sort of the best I could do with buy 200 cheap power supplies and hook them up to each to a power plasma element. But I'm sure in the future you could, of course, engineer something that has is just a one unit with many channels that's more efficient. Yeah, Daniel.
Why did you decide to work on 100 optics?
That's actually a good question. So the reason why we chose 100 is because it was about the order of magnitude that we thought would be feasible experimentally. So, but it also through the exploration that we did with the 100 array where it was all computational, we showed that we could still get some really complex results in device performance with just 100 elements. but we knew that if we were going to scale any further than that, it was going to become unwieldy to build experimentally. But currently, I think like we have the capacity to do 150 elements, but it becomes tricky because you need a stable power source and so if you're plugging all these, if you could plug in, try to use every outlet in the room, I guess, but eventually you get some jitter that can affect your performance.
Any other questions?
I can check
No
the
other
chat one more
family
time.
members? Leanne, here's an opportunity to stick it to him, come in here. No? Okay, if not, I'd like to thank Jesse once again.
Thanks, guys.